Notes 5, limits of transcendental functions. So a transcendental function is a function such as an exponential function, a trig function, and then the inverses of both. So looking at the first part, analyzing limits of exponential functions, remember that the standard form for exponential is y is equal to a times b to the power of x minus h plus k. And there was two types of exponential. We could have an exponential growth and then an exponential decay. So looking at part A for exponential growth, we have the following function and its graph. It wants us to look at the limit as x approaches negative infinity. So that's this side here. As it's approaching negative infinity, notice that we have a horizontal asymptote there. So it's not going to be able to go past that, which means the limit is going to approach negative 3. On the other side, we have the limit as x is approaching positive infinity, so this right side here, and notice that there's an arrow pointing up, so we know that our limit is going to go towards positive infinity. So since we went from negative 3 to positive infinity, this tells us that the function is increasing. Okay. Still on exponential growth, again looking at the graph, if we look as x approaches negative infinity, so that left side, we see that x is, the limit is approaching 2. And the limit as x is approaching positive infinity, on the right side, we see the arrow going down, so the limit is going to be approaching negative infinity. So 2 to negative infinity tells us that we are decreasing. Okay, in part C, same thing. We are looking at the left side for negative infinity, the right side for positive infinity. Looks like on negative infinity, it's approaching 1, and positive infinity is approaching positive infinity, which means that we are increasing. Okay. Now let's look at exponential decay. So on the left side of our function, it looks like our function is approaching infinity. On the right side of our function, it's approaching that horizontal asymptote at negative 3. So from infinity to negative 3, that tells us decreasing. Okay. So on the left side of this function, approaching negative infinity, we're also going to approach negative infinity. And then on the right side, as x is approaching infinity, we notice that our limit is not going to go past that horizontal asymptote of 2. So this is increasing. And then lastly, f, looking at the left side, we see that the function is going towards infinity. And then on the right side, the function is approaching that horizontal asymptote at negative 2, which tells us that it is decreasing. So basically, we saw three things happen here. We saw either it approaches negative infinity, positive infinity, or a asymptote of some sort, y equals b. Okay. In pre-calculus, you learned about the behavior of these exponential functions. So if a is positive and b is greater than 1, then we know that f is increasing and b is an exponential growth. If a is positive but b is between 0 and 1, we know f is decreasing and b is an exponential decay. Okay. So looking at each of these, starting with that first one with growth, we first have to see if b is greater than 1. Well, our base b is the part inside the parentheses. So 3/2 is greater than 1, checks out. And since our value is greater than 1, we move on to the next part, and that is to locate our a value when we're trying to see if our a value is positive. Okay. Since the a value is supposed to be in front of the b value, and we don't see anything there, we're going to assume that we have an invisible 1, so a is equal to 1, which is positive, so that checks out. Then we're going to do is look at the limit as x approaches negative infinity. And every time we did that in the part above, we noticed that it was approaching a horizontal asymptote, or in this case, the k value of the exponential. Okay, so the k value of this exponential is -3. And then lastly, our limit as x is approaching infinity is going to be based off if our function is increasing or decreasing. Well, since a was greater than 0, we knew that this is increasing. And since this is increasing, we know that it's going to be approaching infinity. Okay, so here, these correlate directly with each other. Okay. I'm going to skip down to decay so we can see the difference here. In decay, we're now checking if our b value is between 0 and 1. So our b value here. So we have 1/2, which is between 0 and 1, so that is good. And then again, we're checking to see if our a value is positive. So same as before, we don't see anything there, so we're going to say that a is equal to 1, which is positive. But this time, if we get a positive a value, we're going to be doing the opposite because we're going to do a decay, so this is going to be decreasing. Okay. And then the next part, we're looking at the limit approaches negative infinity. Well, instead of looking at the k value like we did with growth, we're actually going to pay attention to see if it was decreasing or increasing. And if it's decreasing, that tells us we're going to do the opposite, which is go towards infinity. So this is going to be the opposite. So that means these are indirectly related. And then lastly, the limit as x approaches infinity means we're going to be looking at our k value, which in this case is -3. Okay, so what I would do now is pause the video and then come back and check your work. Okay, so here I'm just going to fill in the answers. And this is what should have got for each of these. Notice here that it's 3/2 because this is 2/3 to the -x. So technically this is 2/3 to the -1 power, which means we take the reciprocal, so we get 3/2. And then for the decay, same thing again happens here with our b value. This is technically 2 to the -1 power, which means we take the reciprocal, so this is 1/2. Okay, now let's look at some examples. So in this example, what I would be doing is I would be first deciding if this was a decay, and then tell me if it is increasing or decreasing to help me determine what my limit is going to be. So here, my b value is 0.3, which tells me that this is a decay. My a value is negative, which tells me I am increasing. So if I look back at my table, if I have a decay, but I'm increasing, that means it's going to approach negative infinity, always the opposite. Okay, C. My b value is 3 to the -1, which is 1/3, so this is a decay. And a is negative because it is a -1, so that means I'm going to be increasing again. But notice I'm approaching infinity this time, so I'm going to actually write my limit as my k value, which is -3. Okay, and then I'm going to skip that one real quick and go over here. Okay, for this one, I have my b value to be 1/e, which means it's a decay. And then my a is 1, so since it is positive, and I know this is decreasing, and since it's approaching negative infinity but decreasing, then tells me I'm going to do the opposite. My limit is going to be increasing. For this one, b is equal to 1/3 to the negative 1 power, which is 3, which means this is a growth. A is also less than 0, which tells me we are decreasing. And since x is approaching infinity, I'm going to do the same thing and correlate with decreasing and say it's going to go and approach negative infinity. Okay. For these last two, all we're doing is a direct substitution. Okay. So I have e to the power of 2 minus 3 minus 1, which gives me e to the negative 1 minus 1, or 1 over e minus 1. That is good enough to leave as your answer because on the AP exam, you're not required to simplify. Okay, F, I'm going to do the same thing. I have 1/2 to the power of negative x, so negative 3 minus 1 plus 5. So this is 1/2 to the 3 minus 1 plus 5. So this is 1/2 squared plus 5, which is 1/4 plus 5. And you're, again, okay to leave it like this because you're not required to simplify on the exam. Okay, now let's bring in some trig. So for these, it just wants us to do direct substitution. So cosine of 2 theta, but theta is pi over 3 over pi over 3. Okay. Cosine of 2 times pi over 3 is negative 1/2, and then I just bring down pi over 3. Since I'm dividing by a fraction, I can multiply by its reciprocal. So this is the same as saying negative 1/2 times 3 over pi, which gives me negative 3 over 2 pi. Here I'm plugging in theta. So I have 3 sine squared pi over 2, which I can write as 3 sine pi over 2 squared. So this is 3 times 1 squared, which is 3. Okay, so in those cases, direct substitution work. Now let's look at this one here and try direct substitution again. Okay. So if I do that, I have sine of pi halves minus 1 over cosine of pi halves squared. Well, sine of pi halves is 1, so 1 minus 1 over cosine of pi halves, which is 0, so 0 squared. So I get 0 over 0, which is undefined. If I end up with an answer like this, then this tells me that I can do something else to try to cancel anything out. So when I plug my pi halves back in, I'm able to actually get a limit that would exist. So let's say you had a calculator. Okay. Well, you could put this on the calculator and you would see and get an answer from here. But let's say you don't have a calculator. Okay. So you'd have to remember the trig properties or the trig identities in order to solve this. So if I write the same thing I had above, this was sine of theta minus 1 over cosine of theta, cosine squared theta. Okay. Well, I know that I can rewrite cosine squared theta as 1 minus sine squared theta, because by the trig identity, that's sine squared theta plus cosine squared theta equals 1. Okay. And then I'm just going to leave the numerator the same for now. Well, I can actually factor 1 minus sine squared theta, and I could have that be 1 minus sine theta over 1 plus sine theta. Now here is where I'm going to look at my numerator and see what I can take out so I can end up canceling something from both the numerator and the denominator. Well, if I take out a negative 1, I'm left with negative sine theta plus 1, which is the same as saying 1 minus sine theta. So these would cancel out. And I'm left with negative 1 over 1 plus sine theta. Well, now if I try to take the limit of this, so the limit as theta approaches pi halves of negative 1 over 1 plus sine theta, I actually will get an answer of negative 1 over 1 plus 1, which is negative 1 halves. So we're going to practice that skill in the next part. So here I have the limit of 2 cosine theta cotangent theta. Well, I know that I can rewrite cotangent theta as cosine theta over sine theta, which means I can rewrite this as 2 cosine squared theta over sine theta. Okay. And now if I try to plug in pi halves, I get 2 cosine pi halves squared over sine of pi halves. This gives me 2 times 0 squared over 1, which is 0. And that is okay. I'm allowed to have a limit that is equal to 0. I just don't want to have a limit that has divided by 0, which would leave me undefined. Okay, the next one, I have sine theta cosine theta over tangent theta. Well, tangent theta can be rewritten as sine theta over cosine theta. And if I was to multiply by the reciprocal, what would happen is that the sines would end up canceling out and the cosines would be multiplied together. So I would have cosine squared theta, and if I take the limit of that as theta approaches pi over 4, this would give me cosine pi over 4 theta, cosine pi over 4 squared, which is the square root of 2 over 2 squared, which is 1/2. Okay. And then in part C, I know that cosecant theta is actually 1 over sine theta, which means my sine thetas cancel out, and I'm just left with 1 over 3 theta. So if I take the limit as theta approaches pi, that leaves me with 1 over 3 pi. Okay. So 3 things are ultimately happening here. We have a number value as a possible answer. We have a number being divided by 0, which is undefined, or 0 divided by 0, which is also undefined. Okay? If we get something that is undefined, then we need to first see if we could factor anything, cancel, rationalize, analyze, any possible thing to try to cancel anything out to see if we could get a limit. If we can't and we're left with 0 over 0, then that means we need to inspect one-sided limits. Okay, so we have to look as it approaches from the left and to the right, and we could possibly get infinity, negative infinity, or does not exist. So for now, you guys are going to memorize these special trig limits, and notice that each of them are the limit as theta approaches 0. And we have sine theta over theta, which is going to give us 1, and 1 minus cosine theta over theta, which is going to give us 0. Okay. So what we're going to do is we're going to use a calculator to estimate this. So on Desmos, or your calculator, you would type this function, f of x is equal to sine 2x over x. And you would do the same thing for b, c, and d. And then you are going to create a table and plug in the x values, negative 0.1, negative 0.01, 0, 0.01, and 0.1, and get the following values. What you notice is that as theta approaches 0, and we look at both sides of that, we get the same value. So we can say that our approximate for this is 1.99. Okay? If we don't get the same thing on either side, for example, on B, we end up with 0.044 and negative 0.044. These are not the same, so we cannot say that we have an answer for our limit, so we would say it does not exist. Okay, and you would do the same for each of these, just practicing on your calculator. Okay. But let's say we just use that special limit identity to prove that if we were to rewrite this in a way, we could solve the limit. So remember, the identity above said that as theta approaches 0, sine theta over theta equals 1. Okay, so right now we have sine of 5 theta over 2 theta. That's almost the same, but that 2 on the bottom would have to become a 5 in order for us to cancel it out and say that it's 1. So what I'm going to do is I'm going to manipulate this equation by multiplying by 1, or in other words, 5 over 5. When I do that, I'm left with 15 sine 5 theta over 10 theta, and I can change that 10 theta to be 2 times 5 theta. When I do that, I know that the limit as theta approaches 0 of sine theta over theta is 1, so these would cancel out, and I would be left with 15 over 2 times 1, which is 15 over 2. So the limit as theta approaches 0 of 3 sine 5 theta over 2 theta is 15 over 2. I can do the same thing in B by first using my property of limits that says I can split this into 2 limits. So this is the limit as theta approaches 0 of 1 minus cosine theta over theta, plus the limit as theta approaches 0 of sine 3 theta over theta. Well, we know this is already a property that we talked about above. Okay, we know that the limit as theta approaches 0 of this is going to give us 0. So this is going to go to 0. We know that this very closely looks like our first identity of sine theta over theta. All we're missing here is to multiply or manipulate this by 1 and multiplying by 3 over 3. So we get 0 plus the limit as theta approaches 0 of 3 sine 3 theta over 3 theta. We know this part is going to cancel out to 1. So that means when we're writing our limit, we have 0 plus 3 times 1, which is 3. And then last thing here, let's say neither the trig identities work, okay? None of our special trig limit works. We can't do direct substitution, okay? We can't use any of the limit properties. Well, then what do? Well, we bring back the squeeze theorem, okay? So it says evaluate the limit using the squeeze theorem. Explain why you cannot use the product limit law. So all that it's saying is why can we not split this into 2 limits? So why can I do the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x? Well, the answer to that is simply this part. If I plug in 0 with direct substitution, I get 1 over 0, which is undefined. I cannot find sine of undefined. So we would say we can't use this because the limit as x approaches 0 of sine of 1 over x does not exist. We can't divide by 0. So that's why we have to go and use the squeeze theorem. Well, if we know the range of our original trig function, okay, so in this case, sine is between -1 and 1, then we also know that sine of 1 over x is going to be within that range. So if we multiply every part by x squared and use the squeeze theorem, we will be able to get the limit. So this is saying -1 less than or equal to sine x less than or equal to 1 is the same as saying -1 less than or equal to sine over 1 over x less than or equal to 1. If I multiply each part by x squared, I get negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared. And then I take the limit of only the outside ones as x is approaching 0. So the limit as x approaches 0 of negative x squared gives me 0. And the limit as x approaches 0 of positive x squared also gives me 0. Well, since I get 0 on both ends, I can squeeze that function in between those two functions and by the squeeze theorem say that the limit of x squared sine of 1 over x is also equal to 0. So I would say by squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. And then I can do the same thing here on this one. So I would say that, okay, the range of cosine is the same as sine, so negative 1 less than or equal to cosine x less than or equal to 1. So that's the same as saying cosine of 1 over x squared. Multiply everything by x squared. And then look, notice my inside function now matches the original function I was trying to get. And then I take the limit as x approaches 0 of both ends. And I get 0 for both. So by the squeeze theorem, the limit as x approaches 0 of x squared cosine 1 over x squared is also equal to 0.